With the increase in sustainability initiatives and the push toward bioplastics derived from biomass, we're demonstrating that we can harvest from insects the building blocks from which we can produce degradable polymer materials as next generation products and plastics.
Hello, I'm Sophie Rovner from the American Chemical Society. Welcome to this media briefing from ACS Fall 2023. Imagine using insects as a source of chemicals to make plastics that can biodegrade later with the help of that very same type of bug. That concept is closer to reality than you might expect. Now, researchers at the meeting are describing their progress to date, including isolation and purification of insect-derived chemicals and their conversion into functional bioplastics. To tell us more about this, we're joined today by Karen Woolley and Cassidy Tibbetts from Texas A&M University. Thank you for joining us.
Thank you very much.
Thank you for having us.
What is your overall goal with this project?
Our absolute dream is to set up a cyclical system where we can harvest building blocks from black soldier flies, transform them into functional, high-end plastic materials. And then when those plastic materials are, say, discarded in the environment, they can be broken down by ingestion by the black soldier flies or other species. And then in the case of the black soldier flies, we could collect their carcasses again and harvest new building blocks from which we can make new plastic materials in a complete circularity.
Where did you get the idea to do this project?
We didn't actually come up with the idea for this project. It came from a colleague, Jeff Tomberlin. He's a faculty member in the Department of Entomology, and he's been studying black soldier flies for decades. He was telling us about how the black soldier fly as an agricultural crop is growing enormously, and it's the larvae that are of interest for feed and food and agriculture and ultimately toward humans. The adults simply live for a few days to reproduce, and then they accumulate as waste.
And why are black soldier flies in particular used for feed? Is there something special about them?
What we do know about black soldier flies is that they require relatively low amounts of land, water, and other resources for farming. They have very short life cycles with high yields, and the larvae in particular are very high in protein, essential fatty acids, and other nutrients that make them really desirable for feed and food. The farming and harvesting of them is particularly easy as well and cost efficient and can be applied across the world with minimal resources. The adults are required for reproduction. However, they have a very short lifespan as they only live about a week to mate and lay eggs, and then they are essentially waste.
In your research with the flies, what did you do and what are your results so far?
So far, we've isolated chitin in about 6% yield using a 4-step process. The first step is we take the whole fly and we rinse and clean it, and then we dry it and grind it to give us a powder. This powder we then treat with acid for demineralization, followed by a deproteinization using base, and finally a decolorization using bleach to give us this white chitin product.
So that's the starting point. And after harvesting the chitin, then Cassidy's been working with another PhD student, Hongming Guo, on transforming that chitin to a chitosan and then doing a reaction to install functional groups that will allow for cross-linking and produce a superabsorbent hydrogel material. Those superabsorbent hydrogels are biodegradable, and they're also able to capture water fast in about 1 minute and 47 times their mass. So they have high capacity, fast recovery, and we anticipate that they might be useful in preventing flooding situations, retaining that water and releasing it with the release of the nutrients that were in the original chitin to allow for mediation of the effects of drought and even growth of plants as new food sources.
And what are the implications of your findings?
I would say the primary implications from our findings are that the vast array of biomass sources is expanding. So for many years, people thought they had to use, say, sugarcane or cellulose from trees and harvest materials from that to build synthetic materials. There's a lot of work on algae, and now we're showing that even flies can be used as a source from which plastics can be derived. And the thing about building those plastics up is we're building in linkages that we can break back down. So these materials are meant to be not only degradable if they're lost in the environment, but also digestible. If humans collect them and sort them for processing, they can be recycled. So there's so many vast implications from the sourcing to the end application that brings in things like sustainability and addressing plastics pollution.
And our use of the adults in particular is helping to close that circular economy for the black soldier fly.
Yeah, and speaking about closing the circularity, we're super excited about taking a look at the nutritional benefits of these plastics that are synthesized from the components that come from the initial adult flies, and seeing whether the larva can eat those plastics and then break them down and regenerate new building blocks that we could harvest to make new plastic materials. And so the circularity just goes round and around.
All right, and tell me a little bit more about the products that could be made from your insect ingredients.
So the applications for chitin are pretty much endless because it can be transformed into chitosan, both of which have massive uses in pretty much every industry, from medical, cosmetic, as well as plastics. And so right now we're focusing on the super absorbent hydrogels, but the applications are truly endless.
And that's just for the chitin, the polysaccharide that's abundant in the flies. As Cassidy mentioned, there are also lipids and proteins and other components that we can harvest from the flies in later stages. Right now, we're excited about breaking down the chitin into small molecules, including glucosamine, and building that back up into, say, polycarbonates that could replace bisphenol A polycarbonate and other engineering plastics.
And how does your work differ from that of other groups that are developing products from insects?
The key thing that we are using is the adult black soldier fly. So most other groups researching using insects, especially black soldier flies, are using the larva or the prepupa. We're using the adult because they are a waste stream right now, and so that's really critical in order to not compete with the use of the black soldier fly in feed and food. Additionally, we are looking into rigorous characterization at every step to fully understand the extraction process and the chemicals we're getting out.
And you mentioned chitin from shrimp and crab shells. That's already used commercially. So what's it used for, and what's the advantage of your chitin?
Yeah, as Cassidy mentioned, chitin is used in a lot of different applications. It's a little bit tricky to work with because it doesn't have high solubility. It's more soluble than, say, cellulose, so that makes it a little easier to work with. When it's deacetylated or partially deacetylated, it opens up amino groups that bring in unique properties. We, in fact, have studied that as a bioabsorbable and hemostatic agent that can clot blood rapidly and undergo bioabsorption later. That's not novel either. Other people have looked into that as well. So, as Cassidy mentioned, from the medical field to coatings to cosmetics, there are many different directions. I want to emphasize that we're at a really early stage. We're harvesting the chitin, we're optimizing the conditions for that harvesting. As Cassidy mentioned, we're undergoing rigorous characterization of the materials at each stage, from the initial rinsing and drying to the demineralization, to the deproteinization, to the bleaching or decolorization steps, and then further doing chemical modification on that to make it ready for being put into place as a super absorbent hydrogel. So each of those steps takes a lot of chemistry, which is why we're happy to tag team our presentations at the American Chemical Society meeting.
We are also making sure to focus on procedures that are very scalable, because the black soldier fly adult waste is a significant quantity, and we want to be able to find a process that is able to make use of that in large quantities, because also the chitin yield is currently only at 6% and probably maximum in 8 to 10 based on previous literature for what is in the adult fly. So you will need a large amount of the flies to get a good quantity of the chitin. And so we're making sure to really characterize our chemicals that we're getting out, as well as keeping the process truly scalable.
All right, well, thank you, Karen and Cassidy, for sharing your research with us.
Thank you very much for having us.
Be sure to check out our other media briefings for ACS Fall 2023, which will be posted throughout the meeting at www.acs.org/ACS Fall 2023 briefings.